What happens when the content AI models train on becomes increasingly filled with AI-generated data?
I'm Vedita, Sawhney, and I worked with Jackson Brown and Sean Thompson under the guidance of our coach, Dr. Mayer, as part of Team 1019.
And in this project, we like to discuss model collapse, the phenomenon where, through generations of training on large data sets and putting information back into those data sets, AI-generated content gradually loses diversity and fidelity as it drifts away from the original human data. Throughout this project, we treat content as a sort of probability distribution over features or types. Each generation of AI models transforms that distribution, and we represent the transformation itself as a regression or kernel mapping estimated from a small sample from the data set. We feel this philosophy accurately represents the way that LLMs are designed to predict the next token in a series of tokens, and it allows us to move seamlessly between discrete models, where we track empirical distributions of content types, and continuous kernel-based models where the evolution of the distribution is described mathematically. We begin with a very simple discrete simulation, which serves as the foundation for more complex models later, but it will allow us to quickly see the basic results of model collapse. Each generation, the AI produces new data from its current distribution. We then mix in a fraction alpha of human data to see how external input influences stability. Finally, we resample a small number of examples, 30 per generation, to form the next generation's distribution. This recursive process is repeated about 50 times and captures both the noise introduced by finite sampling and the stabilizing effect of human input. Running the simulation reveals some clear patterns that depend on the fraction of human data injected in each generation. With no human input, as seen in the leftmost graph, the AI quickly converges to just a few dominant content types. Most of the original diversity is lost, and the system rapidly becomes homogeneous. With greater amounts of human input, collapse still occurs to some degree, but more gradually and to a lesser degree. Some of the less common content types still become extinct, but more persist for longer, showing that even the small presence of human-generated data slows the homogenization process. With more substantial human input retained, 10%, we can see that the concentration rises only to 0.3 above the baseline rate of 0.2, compared to the dramatic 0.8 it rises to after only 50 generations with no human input.
So our model is based around latent spaces, and this is basically a way to represent words in a language and the relationships between those words, which can kind of fully encode language itself. So it does this by representing each word as an item embedded in a manifold at some location. And then in the manifold, spatial distance represents how similar two words are in a certain sense. This is a very simple case, of course. It's just 2 dimensions. And in practice, this is not enough to encode the relationships between all the words of a language. So in reality, we use much higher dimensional spaces. On the right, there's a more realistic example of what this might actually look like. So now on to the model itself. On the left-hand side, there's a differential operator and then rho. And rho is a function of x and t, and it represents the density of an item x, like the number of occurrences of it in some data set. So basically just measures the proportion of the data set that is x, where x is just some entry in it, like some just piece of text or something. And then obviously the delta, or the partial operator, is just a change in that. So it's a differential equation. We're measuring the change in the density of x in the data set. There's 2 terms to this, the A term and the B term. A is the AI produced component of the change, and then B is the human produced component of the change. So A and B are coefficients that just measure the strength of the production of each of these. So A is the strength of LLM production, and this is kind of the root of this equation. And it's an integral of a kernel times the density at y. So the kernel is the k. You can think of it as a function that takes in x and y. And basically, it encodes the probability of some artificial intelligence producing an entry x when given a y. So large language models will take in data and then produce data, right? So k kind of encodes the probability of producing x for some given y. And you can see that in the integral, the kernel is multiplied by rho, the rho of y of t. And this is because not all densities of some item y are equally prevalent, so we want to kind of weight the sum kind of to accurately describe the total probability of x being generated by AI, which is what that term describes. And then this mass conservation term, you can see it's present in both the AI and human generated changes to the components of the change in probability for x. So you can think of this as kind of our attempt to normalize what we're talking about, normalize the densities, the quantities, because in reality, AI content is being added to the data set, and then human content is being added to the data set. So if we're measuring pure quantity of data, then it'll just rapidly rise. But that's not always like easiest to deal with. And even in like the real world, obviously the internet is continuing to get bigger, but when you take samples, the only important information is about like proportions and percentages, because like with a fixed sample size, no matter how big it is, the proportions are the only thing that's going to matter. So this is kind of our attempt to normalize it, to discuss proportions of densities and not just densities and total quantity of data. So this is just like subtracting out the current amount of how it will change. So yeah, it's just our attempt to normalize it. And then moving on to the human term. B is just the coefficient of like the strength of human production, so the quantity of human output being put back into the data set. And then this is just the placeholder of like how much X will be produced, so pretty simple. And then we have the same mass conservation term.
We then used our mathematical model to conduct further simulations, this time by using mathematical functions to represent the kernel. A kernel function maps the probability that one data sample maps to another. The first kernel function we considered was the radial basis function kernel, which is one of the most commonly used kernel functions. It uses the Euclidean distance between two data points, which is shown here as r, to measure the similarity between data points. We then considered the Matern 3/2 kernel function. The Matern kernel is more flexible and incorporates a parameter that allowed us to control the smoothness of the function. The 3/2 in the Matern 3/2 kernel represents the smoothness. We chose an intermediate level of smoothness since the higher level of smoothness in the Matern 5/2 kernel could lead to greater loss of the original data. We used the values of the kernel and the related Gaussian process mean function to calculate an expression for the kernel that we used in our code. Here is a graph of rho, which is a probability density function we used that was composed of 3 different normal distributions. We used 2-dimensional normal distributions to represent our data for simplicity. We started with 900 data points that were randomly sampled from rho, and we used these to calculate the Euclidean distances, also known as r, in our kernel functions. We use a mathematical definition of rho in our following calculations, where we calculated the change in rho over time, over one time step before changing rho accordingly and then recalculating. We repeated this process for 5 generations, ensuring that we scaled the resulting distributions so that they represented probability distributions, and we used MATLAB to conduct these simulations. We began by considering the radial basis function. The blue line represents our initial rho function, which was based on 3 normal distributions. The generations are shown in order from red to green. With each successive generation, values that were less frequent in the original data became less frequent in the distributions, while values that were more frequent in the original data became more frequent in the distributions. This disparity can be seen in the peak at 7, which more than doubled its frequency over the 5 generations. The Matern 3/2 kernel showed a similar pattern, but it displayed even greater variation from the original data. This was surprising to us as we had expected the greater flexibility and smoothness of the Matern 3/2 kernel to better preserve the frequencies of the original data. In both kernels, we used a value of 0.9 for the strength of LLM production and 0.1 for the strength of human-generated content. We then combined both kernels in our final model, which represented the interactions of 2 AI models. We used values of 0.45 for the strength of AI generation for each model. The strength of human-generated content was again 0.1. We observed much less deviation from the original distributions than we had observed when considering singular kernels. After considering our various models, our major findings were that when multiple AI models interact in the presence of new content that is generated by people, as well as content generated by other AI models, new content will eventually converge onto certain areas, which will be mitigated by the creation of human-generated content. The long-term pattern will be that AI models will lose the variation found in human-generated content. As a result, the quality of AI model results will decline, but this decline will be slower if more AI models are interacting, since AI model interaction somewhat preserves the original data and may mitigate the impact of AI model collapse. Our model could be improved by representing higher dimensional data, by using more kernels, and by considering the long-term effects of AI model collapse. Thank you for listening.